Bonjour et merci. I'm going to speak in English, mostly for your benefit. I'll try to speak clearly and not too fast. So, yes, my name is Jessie Abbate, and I am actually an infectious disease ecologist and epidemiologist. And I joined not too long ago Geomatys, which, thank you for the introduction, is well, you can't see it here because of the affichage, but it is a company that is specialized in that is well known, maybe you might not know of it, but it is well recognized as an innovative company doing a very highly trained and doing a lot in the field of geospatial data processing and analytics and infrastructure, so data infrastructures. And so I came there to build a project called Project Epwise, which you can see here. Oh, oops. Which is focused, it's going to be a spinoff that will be focused on taking these technologies that we've been talking about today, largely in the field of geospatial data, big data, and making that more accessible and operational in the field of emerging infectious diseases, especially those that have a lot of climate sensitivity or require a One Health context in order to manage them. So it's not entirely, so I'm located in Montpellier, in our building here. It's not entirely, I don't know if there's oh yes. So it's not entirely random that it's located here. These are the Geomatys was actually created by researchers who were previously at the MTD, la Maison de la Télédétection, and that is actually one of the centers for the development, many really great researchers working on the field of tele-epidemiology, which in English we don't even have much of a word for that that's as compelling, but it's basically remote sensing for epidemiology. And so it's really, the idea is to really bring this academic field to an operational and much more widely accessible audience. So what is a One Health context? So, oh, I have it here. That's why everyone's looking down. So about 60 to 75% of emerging infectious diseases are zoonotic or of animal origin. And climate sensitive diseases, of course, especially in temperate zones such as in Europe, are expected to rise with the changes in both climate and other global changes. And so the idea of One Health is that we, especially for zoonotic diseases, the idea is that to manage and mitigate these diseases, you really have to consider the entire system. So the environment that might provoke the emergence or the interaction between animals and humans, and also the health of the animals or how animal populations are managed, and also wildlife. And so putting those things together is actually one of the big, it's the big, the point of PREZODE, which if you haven't heard of that, that's the Predicting Zoonotic Disease Emergence. It's a large consortium project that is working to do that. And we happen to be in the same building now with one of their centers. And so the idea is really we're helping with bringing together these very diverse data sources that come from very different fields. And doing that is a technical challenge. And so that's how we're contributing there. So I'm really going to talk about how we use a lot of these products that Laura mentioned earlier with geospatial AI and how those products can be used for epidemiology. And so, sorry, I'm a little bit perturbed. So the top should say These are the resources that we get from Geospatial AI. And so Geospatial AI, as you've heard already, gives a lot of information from Earth observations. So I'll be talking mostly about Earth observations, such as extracting physical features, such as roads and other pathways for movement. But also land cover, land use, and a number of environmental factors. And so both the physical extraction as well as the spatiotemporal multispectral analyses that, for instance, Matthew was just talking about, that allow you to analyze these really large data sets. They really rely heavily on AI or machine learning processes. But also, as we were talking about earlier, geolocalized contextual information is really important for surveillance, such as the project PADIWeb from the CIRAD, as well as the EIOS system from World Health Organization, which is the epidemic intelligence from open sources, one of the two. And also syndromic surveillance and other behavioral factors that we can get from, say, Google searches and those types of things, which use large language models to extract information. So how we structure these disease models is that, of course, they can be first based on surveillance data, so data of the disease occurrences, in order to understand how where the risk is now and in the future, especially with climate change. But we definitely need a lot of information that doesn't actually relate to cases of the disease at all. So those things are such things as host and vector habitat suitability. What factors really affect how large and how distributed those populations are. Then interactions between the host and humans. So at the human host interface, at the human animal interface, what kind of factors are contributing to spillover events? And then of course, human to human interaction, that tells you like how it's going to spread once it comes over from animal populations. And this allows us to do disease risk mapping and scenario modeling in order to give disease risk stratifications, forecasts, and alerts, those types of things, which then can be used by decision makers. And so space assets, which we have a large part of our funding comes from the European Space Agency and the CNES. So these satellite imagery and other space assets are really important for us because they can be used to update the models more regularly and more quickly than if we had to gather the data from governments, for instance. And it also allows us to extract the information in areas, especially in the global south, where we might not have those data, or they may be really poorly distributed. And so climate and land use, habitat change, habitat encroachment, human densities, transport routes, those types of things are really important to inform these models. And so I'm going to walk you through an example, and this is not maybe too relevant to France because it's Ebola, but it's one that we're currently working on. And we're also working on dengue. So you can imagine that this model actually can apply to many different situations and different diseases. And so, and I will add here that that these types of models, we typically, if we have a lot of information, such as dengue, we know where dengue cases have happened. They've happened for, many decades. Well, not that many decades, but they have happened. There's a lot of data out there. We can use machine learning methods. But in general, when we're talking about emerging diseases, we don't have that much data. And so we're talking about using mechanistic models, which also have the advantage of being able to tell us which part of the system is really impacting the emergence. And so, so it's nice. We do work with machine learning models, as Matthew was talking about, that do give some inference into which factors are the most important. But for a large part, such as for Ebola, we use a mechanistic model. That said, for one of the first factors I'll talk about is that Ebola's natural animal hosts. Noted, we don't exactly know which animal hosts they really are, but we have a good guess. And those hosts animals have distinct and predictable habitats. And so putting together the habitat suitability from land cover, land use, urban, the built environment, and also obviously the climatic variables, along with the species occurrence from GBIF, which, if you don't know, that's a global database for biodiversity. And there's enough data there that we can actually use machine learning models, so boosted regression trees and maximum entropy, to predict where those animals are to be, and that can be either yearly. It depends on the input data that we have. So having more information, better AI models that allow us to have much more precise data, and at different types of the year allow us to have like monthly spillover risks for where those animals are. And so, and there's some great, what I'm presenting here is a lot of work that our collaborators have done. And so definitely note down the references. These are some great researchers. We also know that Ebola emergence is tightly correlated to forest disturbance. So you can see outbreak number 11 is pretty much the only one outbreak number 11 is pretty much the only one that did not occur in an area. So on the left, I forgot to put the dates, but I think it's something like 2002 and 2009 on the right. You can see that the change, there's a lot of fragmentation in the forest that has occurred, and that's really where you see the outbreaks occurring. And this can be because people are moving into the forest, but it can also be that the habitat is disrupted. So the animals, they may move to different locations. They may be stressed, and when animals are stressed, there's a large theory around them shedding actually more virus when they're stressed. And so that can increase the risk for spillover events. So this is something that's really important for being able to predict where we might expect risk to be. We also know that humans have to be there in order for there to be a spillover event. And many of the human populations that we worry about for Ebola emergence especially is that those human populations are poorly documented, either because of conflict or just because of resources in the country. And so getting really good information from satellite imagery, so from the built environment particularly, is a really big asset. So so you can see here, this is a study that was done recently showing the differences in different AI models and how well they replicate the real world. So those are really important, not just for knowing which spillover events occur, but also density, the population density, how it affects how fast a disease will spread. And it also can impact how people move, whether people move. And so those are really big and important factors in our models. And yep. And I'm almost done, actually. So predicting the spread is, of course, important for both planning and for response activities. And so having a good measure of movement, of human movement, requires data, and from places that we might not have that information, and for places that may, for instance, in the rainy season versus the dry season, may have very different networks of how people can move within a country. So being able to extract that information and across time is really important for understanding how the pathogen will then spread. And so on the right, you see one of the models that we're using for Ebola. That's a mechanistic model if you don't know them, and it really is a spatially explicit model. So we can actually run simulations and tell where we expect the disease to come out of the animal populations and then move. So this is really useful for planning and also for responses. So in general, so Project Epywise within Geomatys, we are preparing for these models that are largely stay within a journal, or maybe a small tool that might be really useful. Like, for instance, Arbocarto is being used across France for dengue and other arboviruses. But what we're trying to do is build a database of as many pathogens that we can, and put them all together, and bring in all of these new data sets, like the Meta's Segment Anything, fire data from NASA. And so this requires distributed computing, geospatial data lake organization, and automated aggregation and downscaling that will all help to integrate this information and make it quick, right? So make it efficient, because it's costly otherwise. And so that's what we're trying to do, is really make a platform for the integration, accessibility, and how can I say that word? Operationalization, thank you, of this really useful information. So with that, thank you very much. Check out our project, and also our collaborators from France and abroad, and we hope to have more to show you in the very, very near future.